Okay, hi, all right. Math 2504, 5 in the afternoon in Brisbane. Anybody here in the non-Brisbane time zone, please say so on the chat. Everybody in the room, you're in the Brisbane time zone. So my name's Yoni Nazarathi. This is Paul Bellet, Paul Verbeek, and Andy Ferris. And soon everybody will introduce themselves a bit more, and we've got some great tutors here too. And welcome to the first edition of this course. The first time we're also teaching in hybrid mode, meaning home and a classroom and many nice screens. Let's hope it's not just 1 or 2 or 3 instances before we lock down, but we don't know. So I'll tell you a bit about the course and run a few things today, and then the staff will introduce themselves as well. And then later on, Paul will take over with most of Unit 1, and we'll take it from there. Interject with questions from home or from the class at any point. I guess I can take this off because I'm speaking. All right, so you could see, I guess I'll go to this website here. So you've seen the course website. I think you kind of know what it's about. Our general point is to actually empower mathematics students, statistics students, sometimes a bit of physics students. Oh, thanks, Paul, perfect. A bit of physics students with programming ability. Now, many of you, according to the survey, you've done programming in different places, Math 1051, 1071, 1072, Sci 1000, Sci 1001. Some of you are doing a dual degree with computer science. Who, by the way, is doing a dual degree with computer science? So we see here. And at home, go ahead and say like, yes, yes on the chat. So not too many. Okay. And the idea of this course, it was introduced into the program so that when you finish in a few years, you'll be more employable with all the math and stat skills that you're picking up will be empowered with programming skills, and you'll end up like perhaps like our great industry lecturers, Andy and Paul Bellet, that have they both have PhDs in physics, math, and work in industry. But even without a PhD, hopefully it empowers you. Also, if you continue and do an honors degree or a higher research degree, just getting more programming skills. Having said that, we're not going to take it slow. We're actually going to take it fast. So we're going to take it quite fast in the lectures, a bit slower in the practicals. The assumption here is that you've done quite a few courses previously. You know how to study, you know how to think, and you're willing to work hard and do it. Now, I must say that in terms of assessment, so I'm not going to go over all of this because you've read probably the course website, and if you haven't, you can. In terms of assessment, look, there's only one quiz. So only one piece of assessment that's actually a high variance component, a component where you come to the assessment and you can succeed or not, and sometimes there's an element of luck. The rest of the assessment is all about hard work and sweat and putting in the time. So in a sense, this is a course that requires a bit more work perhaps than other courses, or so this is the first edition, so we're trying to make it like that. But ideally, it has a bit less variance, because when you hand in your homeworks or your projects, then you know if you've done well or not. Okay, so before we move to a bit more admin, let's just, I'll tell you just another word about me. So I'm an associate professor at UQ. I worked as a software developer years ago before PhD. That was in what's called an embedded system environment. So that was software that ran in wireless radios of jets. But since then, software has moved so much, and now there's GitHub and source control and languages like Julia and all kinds of things. And I'm coming back into the software world in the last couple of years because most of my research work is in stochastic systems. So that's me, and I'll mute, and we'll take it from here.
Hi, my name is Paul Verbeek. I just got hired here back in November. I come from the University of Toronto, which is in Canada. I'm teaching computer science in the engineering department. And the experience that I bring is I used to work for a company called Maple. Perhaps some of you have heard of it, or Mathematica. I'm going to be showing you how to develop tools for pure mathematicians and demonstrate that pure mathematicians also need software. So I'm keen to see all of you in my module, the computer algebra module.
Hi, everyone. I'm Paul. This is confusing because he's Paul too. I guess I'm a lapsed applied mathematician, and I've been working in industry for too long. I'm old now. I'm middle-aged. Yeah, so it's like, hopefully it's an interesting opportunity for me to come back and experience imposter syndrome. But we can, I'm trying to make jokes. Not working.
We're all middle-aged except for Paul and the tutor, so it's
Yeah,
okay.
yeah.
So, okay, we can laugh, by the way, and this is computer science humor. It's
Yeah.
kind of geeky. It goes together with the programming.
Yeah. Okay. Yeah, so I've been out in industry. I've got an academic background, coming out into software. So hopefully I can pass on some ideas about, how it works when you get out, and hopefully give some insight into the types of things you need to know, what's useful and what's not, what you'll bring when you come out. That's probably the most important thing. Since leaving academia, I left for a startup called Roams. They got sold to a big company. I got sick of it, left, went to another startup. I took Andy with me, so that's basically my professional career. Yeah, look forward to teaching you guys. Be kind to me because I'm an amateur.
Hi everyone, I'm not Paul, I'm Andy. My history is I was a physicist here at UQ, did PhD here and did some postdocs overseas before coming back to work for the first startup that Paul mentioned called Roams, which is a geospatial company. And since then moved on to more economic modeling with our another startup called Alara, which is lots of fun. So yeah, it's I'm really looking forward to this course. I think it'll be great. Yeah.
Thanks, Andy. Yeah, okay, so thanks. So we also have some tutors here, and I think some at home. So those at home prepare too. So go ahead, Tom.
Yeah, hi, I'm Tom. I'm in my 4th year of math and CS here. I've been tutoring math for a few years now, and also a bit of computer science. I guess this course sort of combines the things I'm interested in, so I'm quite excited for it.
Hello, everyone. I'm Tina. I'm studying software engineering and physics. And this year I'm doing my thesis, which is in network security.
Hey everyone, I'm Elaine. I recently graduated from a Bachelor of Mathematics honours. I did my honours in mathematical biology, and I got to use Julia a bit in that work, so I'm pretty excited to get to teach it to you guys.
Hey everyone, I'm Jesse. I'm a 4th year math and physics student. I've been tutoring for quite a while now, so I've probably seen some of you guys around in maybe MATLabs or something.
Thanks, Jesse. And Thomas Graham, are you home?
Yes, I am.
All right.
Yep. Yes. Okay. Sorry, everyone. I'm Thomas. I couldn't come in. I had a haircut that got rescheduled. But so I'm recently graduated as well. I did advanced science in mathematics, and so I got to recently experience working with Julia on the Safe Blues project with Yoni. So yeah, I enjoyed it. I hope you do too.
Thanks, Thomas. So Thomas is our coordinating tutor. You could meet him in the first week or two during the visit hour as well, the consultation hour. So the consultation hour is on Wednesday. There's a link on the Blackboard site. Thomas will also be there, and for the few of you, so this lecture consultation hour. So typically he'll have the lecture, he'll have the lecture that's running that module. So we're starting with Paul Billett. Thanks. But also for the first week or two, you'll see Thomas there. And if you can go to a breakout room. If you're having trouble installing, there are a few questions on Piazza. Thomas can help directly. So that's us, that's the teaching team. You'll also see during the semester 3 incredible individuals. So Amy Chan and Metha Matili, or Matili Metha and Anna. So they'll give perspective lectures, and just so there's a bit of value on that, you'll write a little paragraph about their perspective lecture also in the assessment. It'll be like a tag along to the assessment. So the 3 of them, like Andy and Paul, are working in industry, and you could get some perspective on the interface of mathematics and programming that you have from each of them. And I'm sure that that Paul Bellett, when I say Paul, I meant here Paul Bellett, that's going to pick up lecturing today. I'm sure that you'll get a lot of insight from Paul and Andy based on their industrial experience during this course. So feel free to to engage, ask questions. Are there any questions so far? And there's a question on the chat. Hi guys, I was a tad late, not a problem. Is the prac on Friday on? Yes, yes. So let's look at the schedule. So just so we're clear about the schedule. So we've got here the weekly schedule. It should be quite self-evident. You've got the Monday lecture here. You've got the Tuesday lecture that's in the room just across. Oh yeah, sorry, thanks. Thanks a lot. All right, so yeah, and you've got practicals not in every week. So what we're doing in the first couple of weeks in practicals A through D is kind of, you're doing a crash course on this specific language. It happens to be Julia for this course, plus you'll get general computer science and programming background. That's kind of up to prac D. And you see there's breaks. So in week 3, there's no practical. And week 6 and 7, there's no practicals. And then pracs E, F, and G each accompany your projects and help you work through those projects. Now, these projects are going to be sizable. They'll be, and the first project will be out soon. The homework's out already, but first project will be out. So the projects will involve, you'll do things that involve multiple modules, multiple files, etc. Some of this, so that's in terms of schedule. So yes, there is a prac on Friday. The only prac that's actually going on to be, as we said in the message today, the only prac that's going to be put on Blackboard is the 4 to 5 p.m. Brisbane time prac on Thursday. That's the external prac. Everybody can listen to this prac. It's not going to be on YouTube. It'll be on Echoes 360, so you don't need to worry about being anonymized or not, stuff like that in this prac. I guess with this, well, let's worry about that later. Okay, and of course, if we lock down, all pracs will immediately become Zoom, and we're all well practiced with that. Frankly, almost a bit more practice than standing in front of a real class. But even though I can't see your beautiful smiles, it's still nice to stand in front of a class. Some things are in pairs. So you've got the first homework is in pairs, and the second and project number 2 is in pairs, as you can see. So the idea of working in pairs is not it's not a matter of reducing marking workload. It's actually a matter of helping each other. So as you'll probably hear more and more from Paul Bellett and Andy, and also Paul Verbeek, he also worked in Maple. You know, software development you're rarely a sole wolf. You work with other people, so you'll start on that already with homework number 1. Now, another reason to start homework number 1 in pairs, this is homework number 1, which you can look at, is there's a lot of variability in what you know and what others know, etc. So in the first homework, you'll be able to help each other more. Okay, whereas homework number 2 is individual and the quiz is clearly individual, etc. The quiz is currently scheduled as being here, but we might actually just do a Zoom quiz. It'll be also more equitable to those at home, and we'll see how we do it. So excuse me if we change the quiz. In terms of handing instructions, there'll be a bit more information. But basically, from homework number 2 onwards, what you're going to hand in is, you're always going to hand in some PDF file into Blackboard. That's kind of where the markers can also give you feedback. But you're going to create GitHub repositories from homework 2 downwards. Homework 1 is just going to be a PDF file, and your code in Jupyter that you hand in. I like this idea. I've been doing it for a few semesters with other courses. With each hand in, you need to make a little voice recording and upload a voice recording where you say, hello, my name is Mrs. Fu Bar, and this is my own work, except for bits that I consulted with that and that and that. And my experience was that I hated this assignment, or that I loved it, or that I found it good. So that experience recording, we can't promise we'll listen to each of those recordings, but it's also a way of making you a bit more accountable. And often we do listen, the markers do listen while played back as they're looking at your assignment. Any questions? No? Okay, so we're ready to get to it. So look, what I'm going to do is I'm going to do something very silly motivational, but then quite quickly actually give things over to Paul Bellett. that's going to run with you. Oh yeah, in the lecture schedule you see, so Paul Bellett is going to run for the first couple of units, and then it'll be myself again, the course coordinator, plus Paul Verbeek, and then and Paul Verbeek's going to be the head honcho here when it comes to computer algebra systems, and then we'll hopefully you're not too tired by the end of semester because Andy is going to come back and you won't see him till then with a lot of power. Paul and Andy work together, as I said. I often, when we Zoom, and all lecturers have been involved in creating this course in the past 8 months. And often when we Zoom, suddenly I see them in a bank or something like that. They don't work in a bank, but they sell to banks, and I guess that's a good thing. So yeah, that's them. All right, so what I'm going to do here on my terminal, so this is a Mac, okay? And if you don't have a Unix or a Mac, a Linux or a Mac, that's perfectly fine. On your Windows machine, as we suggested, install some sort of shell, perhaps. You'll get a shell also with Visual Studio Code, which we asked you to install a bit later, but you can install Git Bash, okay? But in my case, I've actually configured it that if I just write iJulia, what it does is it does the same as running Julia, which I guess I'll do, Julia in this case, and using iJulia. Hit some key, the insert key. That didn't work. Using iJulia and then notebook. Okay, so I won't do that. In my case, you can try and do this yourself, and by the third week you'll do a bit of shell scripts and things like this. So it's iJulia is just a little shell script that does the same thing. So in my system, when I run iJulia, it opens for me Jupyter Notebook. Of course, some of you don't run Julia through the command line. You just go through your launcher or start menu or whatever, and you would run Julia like that. Okay, and there are different ways to run Julia, and that's not the key point. So at this point, I'm just in my home directory, but I'm just going to create a Julia notebook and give it a name. And we should typically upload these things. Now, what we're going to do in most of the lectures is not that we type out everything, although typing, when you see us typing out, it's pretty good because it's roughly at your speed. So the typing out speed of the lecturer or tutor is your speed of following. But quite soon we're going to get to Unit 1, which I will start from. And this has been created. You can find this on GitHub as well. It's created using a tool called Weave. Using Weave. So what I'm going to do is I'm going to run this code, okay? But for this specific thing, so one way I can do it is I can just copy paste it, okay? I can copy paste it, but for this specific thing, I'll do something which is roughly similar, just so we get a bit of a motivating example, okay? I'm not sure how motivating it will be for you, but let's see, okay? So we've got a first of all, I just like doing this. So why do I do this? Somebody would know why I do this thing. Yes, Paul Verbeek. Say again? Yeah. So to right. Okay, for reproducibility. Okay, thanks. All right. So if I do this and then I run rand, I get some random number 0.82, and if I run this thing again and run rand again, I get the same random number. Oh, we'll say, well, it's not random, it's pseudo-random, but you've seen pseudo-random numbers elsewhere. And you'll get more into random numbers in general when Andy kicks in by the second half of the course. Okay, but then I want to do something like data equals rand 100, okay? Not very interesting, but we've got 100 data points, okay? So we've got a 100 data points. Let me just run this after I run the seed, so I'll make sure it's the same one. Okay, and so you've got 100 data points, uniform 0, 1, and I can ask what's the maximum. And by the way, what I'm doing often is I do max and then like EI, then I hit tab and you get autocomplete. So you get this type of autocompletion in Jupyter, you get it in the REPL, you get it in your editors typically, etc. Okay, etc. So the maximum of data, good, is 0.97. I mean, we expect the maximum to be quite close to 1, right? Okay, but let's say we don't have this function maximum, so let's just implement some very silly version of this function. Not that one can do much better. So how would we do that? How would we search for the maximum entry? Well, I guess what we can do is we can just run on the data element by element, And every time we see, oh, if we have a new maximum, oh, we'll keep that as a maximum. So every element of the data will compare to what was the maximum up to there. So let's say we do this and we do, let's write it first not in a function. We'll just write, m will be, and I'll write a comment, will be our maximum. So what should I initialize m as? So I'm going to run and we're going to search for the maximal NON. What should I initialize m as? Any ideas? What should m be initialized as? I'm going to run. Yeah. That's an option. Okay, that's certainly an option. So there was an option. Let's initialize m as the first element. I actually think it's a better option than what was my option. What would be another option? So that's m. What's another option for initialization? I like this one, but a different one. Chat. Oh, -1. Okay, so then we have on the chat, thanks. So we have on the chat -1. So why -1? Because the person that said -1 on the chat knows that the data in this case is constrained to live between 0 and 1. Okay, so we know this thing on the data. Or you could put -epsilon in general, okay, or just 0. But what would be another safe option if we don't know? Well, what we could do is we can do -inf. Is that going to work? Yeah, I think. Okay, so both options, another option. So both your option there and the -inf is fine. And then I guess what we want to do the first time is then we want to get to the. So let's just stay just for purposes with this one on line number 2. So by the way, I toggle line numbers, escape L, and I toggle line numbers. So we go to this -inf, and then we're going to compare the first element. So we can just sort of ask. We'll ask if data 1, the first element, okay, is greater than the maximum. So if we have a new record, right? We're now in the Olympics. People are breaking world records all the time. There's suddenly a new record, okay? Then m equals data 1. Okay, that would see if that happens. What's going to be the value of m after I run this bit of code? I mean, this is not the whole thing for search for maximum, the first step. What's going to be the value of m? I mean, in terms of what is it like? With this initial value, it'll be data 1, like said on the chat, okay? So here's m comma data 1, okay? Let's see the tuple, they're the same thing. Okay, and then, of course, we want to continue. This is very slow, but that's okay. It's good to start slow. All right, so then we do, well, if data 2 is greater than m, then m equals data 2, right? We're comparing the next one, right? And at this point, well, it actually happens that data 2, so if you look at the first 5 elements of data, the second one is greater than the first one. So by the second one, we already had a new record. Okay, great. So we want to continue this again and again. So of course, we're going to wrap it in a loop. So what we can do is we can do for example, I in 1 to length of data. Okay, and then we do this type of thing. And we start again here. Let's just start from the start. M equals -inf. So in a language like Julia, which is in the way I'm interfacing with it now, it's like Python and like R and like MATLAB. You're actually all the time interfacing with something that's running in the background. It's called a kernel. You'll hear much more about that. Okay, and you're all the time changing things. So you're kind of scripting while you're actually developing. But who's programmed here in C#, C++, C, Java? Okay, so Swift, great. Application level languages where you actually create a program and you let it run. Okay, and those guys create an executable. Julia does kind of the best of both worlds because also compiles things that are almost as fast as those things, sometimes as fast, if not faster. But the point is that we're scripting here, okay? That's what it's called. Okay, so for I1 to length data, if data I is greater than n, meaning if, and it's always good to document things, if a new maximum, even though this is a special case, m equals data I. Okay. Will this work? So let's see. So I put some line numbers and then you think about it and then you look at it and you say, okay, you start with -infinity, or we could have started like the gentleman's suggestion with data 1. Both ways to start are nice, okay? And if we start with data 1, by the way, we might as well go from the second data. But let's, we could have put here 2, but we don't want that because if data happen to be of length 1, it won't work. Yes? Okay, so Julia indexes from 1, like MATLAB, okay? And like R, not like Python or JavaScript or C or Swift. Julia indexes from 1, and you know, the world's divided to the people that like this or like that, or you can be one of the people that like both indexing from 0 or 1. Yep, so that was a question. So the question, where does Julia index from, is kind of what's the lowest data? So if you go data 0 on other languages, you'd get the first element, but in Julia, we would get an error. And we want to learn how to read the error. So this is a bounds error attempt to access a 100-element vector at index 0, and we don't index from 0. Okay, so let's see the maximum, and let's check it with the actual maximum function, and that's it. Okay, so we've just implemented the maximum function. Did we implement the maximum function? Was it a function? It wasn't a function, it was a few lines of code that were running here. But then actually what we can do is we can put it in a function that we can call again and again. So let's just copy it and make function my maximum that gets a variable called data. And the name of the variable here has nothing to do with this global variable data there. And let's paste this in. And it's nice in computer programming to indent things. So like you would do in many editors, I do command or control right square arrow, and that indents these things to make it kind of pretty printed. And this is kind of okay, but there's something I don't like in this function. This is a function that does my maximum. What does somebody not like about what this function does? I mean, yes. Sorry, just a bit louder. Right, it just prints, which is kind of okay, but often you'd want to make functions so you could put them in other functions. You want things to return. So if somebody's printing, you want to do that. So let's actually make an agreement with this function. Let's say, let's say, and this is one way to create documentation for the function. We'll put this multi-line string about this function. We'll say, this function returns the maximum of the input data. Okay, and we could do that. So then instead of this line, we'll do here a return M, okay? But in Julia, like in some other languages of this family or this type, you don't need to write a return statement. You can just do that. So after I've run this, I get this output like my maximum. Let's just check a second, my maximum on the data. And it found that same maximum. Good. We know how to program maximum, but that already came for us. Okay, so what I'll do, what you're going to do in the practical this week is actually just work a bit with this Jupyter environment, the REPL environment a bit more. And I suggest, as was said before, that you go to the practical A. So I just clicked here on practical A, and try this even prior to the practical. Okay. Might be a typo or two in there. If you find typos, you can tell us, or soon you might be able to even do a pull request to the GitHub. I mean, you can already, but you might not know how to do it. A pull request to improve the practical. Okay, so that's what you do here. Now, in terms of our mode of teaching, we won't be able to do this all the time because this takes time. Yeah. No. So the question was, does your GitHub account need to be connected to your UQ email? No. So your UQ email is good for grades and hand-in, but GitHub, you can be a completely independent. Yeah, and if somebody has a problem with GitHub, maybe you got kicked out because you were abusing GitHub. I don't know, maybe you're putting cat photos there or something. You can use GitLab or something else. Okay, so we'll work it out, but let us know. Okay, so so that's my maximum. Now, we won't be able to teach like this, typing everything, because things just take time. And the lectures are going to be quite intense, actually. So what we're going to do most of the time, I mean, you'll see that Paul Bellet jumps between code in the REPL and the unit, but a lot of the time we'll use a static unit. Okay, so which you have the code for, by the way, so you can copy this code. But if you go to the course GitHub, you also have the code that created this. Let me actually just show you this very quickly before I move on. So let's just open a new tab for the course. And so here's a GitHub repository for the course. And this GitHub repository, we might get later on a Jupyter version of this course material. At the moment, we don't have it. But if you go here to Markdown, then you've got lecture unit 1, this extension .jmd. This is our code that created the lecture. Okay. Feel free, by the way, to have pull requests on that. So if you find typos or want to correct things, go ahead and do that. Don't feel obligated, obviously. Okay, so, and this is similar. Has anybody here used R Markdown by any chance? Okay, we've got one person who used R Markdown. So it's a way of both creating a formatted story, a static formatted story, and some code. Different from Jupyter, which allows us to to combine formulas and code. Oh, I didn't combine here formulas and code. Well, you'll see that in the practical. Okay, so so here's our story. We've got the maximum of 100 numbers, great. But then here's a question: how many times is a new maximum found? And if any of you are watching the Olympics, you might be interested in this. Like, how many times is kind of a new record appearing? Okay, I mean, you can think of the Olympics as kind of sequential data, and each time the 100 meters is run, and the 100 meters is run, and 100 meters is run. How many times a new maximum is found? So let's look at this code that just augments the function FindMax. So here we call this function FindMax, and it starts with, it puts this other auxiliary information in the function. In this case, is n. So what does n count? Whenever we get this line, if we found a new maximum, we increment n. By the way, we could have just done so if you have x equals 1, you can do x plus equals 1. That's also an increment. There's no x plus plus like you would have in C++ or something like that. That doesn't work. Okay, so that Julia didn't even know it finished the thing. But you can do plus equals 1 for this line. Okay, so you've incremented n. All right. So now the return value here is not just going to be a maximum. It's going to be the maximum value, comma, how many times we found a new maximum. Okay. This is actually in Julia called a tuple. It's a pair of things. Okay, so, and you can, if you've programmed in MATLAB or other languages, you see FindMax returns two things. One of them is a max value, one of them is n. The name of these variables here does not need to agree with the name of these variables here, because the name scope of the function here is just a function. Okay, all right, so in this specific case, there were 4 maximums around the way, 4 in 100, okay? But of course, if we had different data, so let me set the seed for 1. So that's like living in a different universe, and repeat this, then there's going to be 5 along the way. Okay, and who knows? I mean, by the way, what's the chance of having 1 maximum along the way with 100 data points? What's the chance of having a single maximum along the way with 100 data points? What is it? 1%. 1 in 100, exactly. Because the logic of this young man is if we have 100 data points and there was a single maximum along the way, it just means that the minute that, I don't know if the maximum is skateboard flipping score, the minute that sport was invented, the best skateboard flipper ever was in the first one, okay? 1 in 100, okay? So that's the chance of having 1. So then we can ask how many on average? How many are on average? So, of course, what does it mean on average? So you might just run this one on a list, but you can repeat this again and again. How many maxima? What's the expected value of the number of maxima we're going to see? Well, we can kind of compute this for those of you. Who's done here stat 2003 with Professor Cruz? Quite a lot of you. You liked it? I hear a lot of yeses. I'm imagining. No, okay, I like it. Okay, so so what you can do is this typical trick of breaking the number of maxima found into a sum of these indicators. So an indicator is a variable. So now we're in math. We're not in the programming just for a second. Okay, so this variable I1 is going to be 1 if you found the first maximum. If 1 was a new maximum, 0 otherwise. And I2 is going to be 1 if the second element was like a new record, 0 otherwise. So you can say that xn is a sum of these things. Now these variables, they're statistically dependent, but it doesn't matter. Their expectation is a sum of the expectations. If some of the details here are not clear, this is not so critical. This is kind of just so you see a bit of interface of some mathematics and some programming. Okay, but the nice thing is that the expected number of maxima is the expectation of I1 plus the expectation of I2 and the expectation of IN, etc. So the expectation of a variable that gets either 0 or 1 is just the probability of being 1, because it's 1 times the probability of 1 plus 0 times the probability of 0. But who cares about the probability of 0? It's just 1 times the probability of 1. So what you get is that the expected number of maxima is the sum of these probabilities. Now, using the same rationale that the gentleman in the back said, that the chance of in 100 data points to get the first one to be, oh, that wasn't exactly rational. Oh, yeah, okay. Was, yeah, that the first one is a maximum, it's that the first one is a maximum, then the chance of the ith point to be a maximum is 1 on I. Because from an ith point perspective, it just looks at the I points before that. And if you assume, this is under the assumption that data is independent, identically distributed. And it's just a chance that you're exactly on that lucky permutation where, well, on one of several lucky permutations where you are bigger than all the ones before. So the nice thing is that the expected value of the maximum is this thing. What do you call this sum? Well, you see it below. You've seen it everywhere. You like it. It's kind of, it's a nice example in mathematics of a sum where you're summing up a, if n here was going to infinity, you're summing up a sequence of numbers where the ith number does go to 0, but the sum does not converge, right? It's a divergent. If you take limit of this n to infinity, meaning if you put n infinity here, it's a divergent series. It's called the harmonic series, or for finite n, called the harmonic sum. All of you know this, or at least met it here and there in several places. The nice thing is that we can actually say that the harmonic sum is log n, the natural logarithm of n, plus a special constant gamma, which is called the this constant, the Euler, I don't know how to pronounce Mascheroni constant, which is about 0.57. Okay, plus little o of 1, which is something that vanishes. So there's a great approximation for this sum. It just grows like log n. Plus some constant. So if you kind of want to stop here and you want to say something already, you know, maxima grow like log n with the number of trials. So if you just think of it in terms of Olympics, if every time you have, let's say, if you're just looking at Olympic records, every time you're trying something, then the expectation of the maximum is not going to grow linearly. It's going to grow like log n. It's going to grow almost flat, plus a bit of a correction constant, plus a bit of an error term. So then once you get into this, then you can use Julia for numerics. Now, this is a type of stuff that a lot of you have done in other courses. You've done MATLAB numerics. I don't know how effective it was in that first year. A lot of things were happening. You were just out of high school, et cetera, and then getting into the freedom of the new world, and you weren't so excited about MATLAB, fine. But you've done numerics in other courses, et cetera. And the thing is that you now can do, you can compare, say, for example, this Hn, this approximation, which is just this, okay, to, well, or this approximation to the actual Hn, right? So this is code that does this, and I'll skip the details. So in some of the things, we're going to skip the details just to be able to move through the units in due time, and you'll have to read things yourself, okay? So this here is a plot of this little o of 1 term, okay, this term that vanishes. But then we can do more. We can actually do a little Monte Carlo experiment. And when Andy kicks in the third half of the course, doesn't work, the third of the course, I think that's better. When Andy kicks in, you'll do a lot of Monte Carlo, okay? You'll see that, okay, what we're doing here is we're actually doing 100,000 experiments, okay? So we're setting the seed to 100,000 different possible values, each time looking at the maximum, putting these maxima in an array and computing their mean value and even looking at their distribution. We don't care about the distribution, we just want the mean of it, but the mean of it happens to be 5.18 estimated from the Monte Carlo, and the estimate is from this back, well, the approximate approximation is also close to the same value. So that's all I wanted to say here. This is, we can go home. No, I'm joking. But this is kind of the type of things we'll be doing in this course, but only in a slightly more structured and deeper manner, where you have things that are on the one sense a bit algorithmic, on the other a bit mathematical, and little by little you'll be building these pieces together. So are there any questions? Okay, so that was a preamble, and now comes the really good stuff, because Paul will step in. And we're going to do breaks in 10 minutes. So we do kind of 5 till 5:50 Brisbane time, and then 6 till 7 most probably. Thanks. Yeah, I'll just give you this.
Okay. Okay. No worries. Sorry, guys, I'm not very slick. So one of these things you realize when you don't lecture, when you come in, is how slick people like Yoni are, who do it all the time. So give me a bit of patience. I'll be a little bit ropey with things like timing and maybe spending too much. If I'm spending too much time on something that's not so interesting, please feel free to shout out. If there's questions coming up on Zoom that I can't see, or you've got a question, please interrupt, because I'll appreciate it. Yeah, so Yoni gave you a good rough overview of what's happening in Julia. You've seen some syntax, so you probably, learning a new computer language is not like learning a new language. It's not like going from Chinese to French. It's like, it's more like French to Spanish. You've seen one, you've sort of seen most of them, and so hopefully it's not too scary. And Julia is a nice, friendly one, where it's like Python, where the syntax is really friendly and learning curve is low. There's like a lot of depth to what you can go into, but in terms of just hacking around and using it for numerical experiments, it's actually quite a nice language. So does everyone feel pretty comfortable with what you've seen so far? Does it seem pretty good? Feel happy? Good. Good. So yeah, I assume, in the thing, so assuming you've all done Python and MATLAB, and you probably hated MATLAB, and Python's friendly, and you're probably all comfortable with that these days. Yeah, so yeah, that's just assumptions. So, okay. And yeah, if I'm coming in from the outside, I'm not so familiar with the courses you guys have done. So if I'm going in too much laborious detail about something that's easy, please give me a shout out and we'll talk about it. So I'm going to spend a little bit. Zoom much? Okay. Hopefully that's better. Okay. So history. I'm actually probably going to spend too long talking about history because I find this stuff fascinating. Yeah, what's a computer? So, if middle-aged versus, I'm assuming most of you guys are a fair bit younger than me, you would have grown up sort of awash in computers. Like you would have grown up and all fairly fluent with them. Whereas someone like me, maybe Andy too, I guess, with sort of our age, it's like if you're a bit of a nerd, you would have started programming like 10 or 12 on someone's computer that you could find. Internet wasn't really a thing. I remember the first time using a telephone modem to go onto a BBS to download Doom back in like 1994. Yeah, and you had like a big stack of floppy disks. So like, I'm old. It's fun. So, you sort of have this thing of like, it's the substrate of modern life. Like you're so familiar with it that it's not strange. Go back a few generations and it's quite strange. So even this one is like, what's a computer? For the longest time in history, a computer was actually, I got this one, a bunch of people sitting in a room. A human computer. It wasn't actually a device. It was people doing mechanical calculations. So like, it's hard to understand how spoiled we are these days. Simple things were quite difficult. Like, I have a book up the front. I'm not sure driving this, how this is going to work. I might stop sharing my screen and just try and hold it up to the camera. So, this guy. We'll see. I have a book here, sorry. You're welcome to come and have a look. And it is just tables. Oh, do you know how to do it? Yeah. This is called a ready reckoner. So you probably heard about tables of logarithms and tables of trigonometric functions. Have you guys all heard of that as being a thing? This is a bit more everyday. This is called a ready reckoner. This book is something a friend gave to me for a birthday present. It's 130 years old. Well, please feel free to come and have a look at it. What it is for everyday people to do simple sums. Like coming from a time, say 100 years ago, most people couldn't do arithmetic. So they'd have these tables printed, particularly if you're not in decimal. So what this is, let's see if it can latch onto the focus, is for pounds, shillings, and pence. So I don't know how many of you know, like how many pounds are in a, how many shillings are in a pound and how many pence are in a shilling. But if you've got to do fractions, it's just a list from 1/16 of a penny to a pound of fractions. If you need to go like, what's half of 1 pound, 3 shillings, you go look up the page, write it down. Because that math's probably not accessible to most people not that long ago. So life's changed a lot. So I think it's good to know. So human computers, one of the first things I did in Julia language when I was starting to use it, maybe 2014, was to do an algorithm called the Moncrief algorithm, which is linear assignment. So imagine you have 10 people and 10 jobs, and each person's got a particular cost of doing that job. So person 1 doing job 1 would take 10 seconds, person 2 doing job 1 would take 5 seconds. You've got a big matrix of those things, and you go, okay, I'm going to do an assignment of 1 job to 1 person through that matrix and pick the best combination. That Moncrief algorithm is a fast method for doing that. And the paper was written in about, I think, 1940. And it's really strange reading it as a modern person, that it says all these things of like doing prime this row and star this row. And it doesn't quite make sense until you realize that it wasn't for a computer. It was for people actually writing on a bit of paper to implement this algorithm by hand. It was for these people to do. So the world's changed a lot really quickly. And it's hard to understand, how much it's changed. So yeah, as I said, so what's a computer? So this idea that there's this mechanical thing, a mechanical series of steps to do some useful calculation. Don't know how much history you guys know, but like you might say like a simple thing of like a clock, not this one because it's digital, but an analog clock. It's really incrementing a second per second, a minute every 60 seconds, and an hour every 60 minutes. It's a type of calculator. It's a type of computer. It's an analog computer, and the sum is given by gear ratios. So this idea, so like there's some ancient ones that are really quite cool. So probably would have heard about this one, the Antikythera mechanism. Is anyone familiar with that? Yeah, it's found in a shipwreck off the coast of Greece. I think Kythera is an island off Greece, so Antikythera below Kythera. It was for working out the positions of stars in the sky. And so this is like a mechanical calculator for, they think, something like, doing some useful solar calculations. So it's a complicated series of things. Oh, 2,000 years old. I'm not exactly sure. I don't want to say in case I'm wrong, but please feel free to look at Wikipedia and correct everything I say in all these lectures. Yeah, so, these clockwork mechanisms got quite cool. I like these ones, karakuri, little clockwork mechanisms from Japan. They're from like the 17th, 18th century. They would serve tea. They'd be little robots and they'd turn cogs, and you can see this kind of mechanism inside. They had ones in Europe, similar things that could write messages. Quite a high degree of art. You hear of Leonardo da Vinci, people like that doing them as things to show people. So I think that's really awesome. And then the one everybody knows is, we've got this picture over here. Oh, sorry, too many browsers. This picture of Ada Lovelace. Everyone familiar with who she is? The reason, I guess, she's famous is the difference engine. So Charles Babbage was the person who invented the difference engine. Difference engine was for calculating tables, not quite like this ready reckoner one. It was for tables of logarithms and stuff. basically for interpolation. So it does something called Newton's method of divided differences for interpolating a polynomial between some points. So there's some method, I don't know the details because it's pretty arcane now, but you do? Yeah, oh, you're going to get it. Oh, well, yeah. I'm telegraphing here for stuff coming later. I don't know the details of it. Paul does, so that's great. This was for implementing Newton's method of divided differences. So it wasn't a general purpose computer like we think of a computer now. It was a thing that did one thing really well. And that was you could put in an array of things, turn some cogs, and it would spit out the coefficients of the polynomial. So that wasn't the general purpose one. When Charles Babbage didn't get to make it while he was alive, I don't think. He made something called the analytic engine. He had a design for it. And there was an Italian engineer, can't remember his name. He came up with some algorithm on the analytic engine for doing something useful. Again, details are lost to me, but Ada Lovelace turned this into probably the first computer program. So that's a pretty big achievement. And this idea of a stored program separate from the computer is like a really big thing for the start of general purpose computing. Yeah, some other cool things. You know, we always think of a digital computer. This one's a bomb sight, which is a fairly terrible example, but it's a really cool thing. It's an analog computer for working out when do you drop your bomb to hit the target, World War II, but cool technology. The application, not so much. Analog computers have sort of lived on. Maybe you can think of things coming through now as quantum computers as kind of like an analog computer, but there's also general purpose quantum computers coming. People are talking about that sort of stuff. So analog computers are still a thing. We talk about digital computers as we're a thing. I don't know if you guys have seen this. Is from about the 1960s, these things called Curtas. They're like a mechanical calculator that people who did things like the Apollo mission would have used. So we're super spoiled. Like you can start any old computer, do some sums, don't even have to think about it. Something like calculating a function like a tan or a square root is like, back then, much bigger deal than it is now. And you've just got these magic functions in your computer-like programming language of choice that will just, you put it in a thing, get something out. You have no idea about all the arcane things that are going on underneath to make this happen. So back to my point. A computer. So what's a computer? I'd say the answer is it's a thing that was invented for mathematicians and ran away from mathematicians. All these early people, so Ada Lovelace, Charles Babbage, other people who made analog computers back then are people like Pascal and Descartes. So you know of those from mathematicians. All the early pioneers of computer science were mathematicians. The current architecture of a stored program computer, the von Neumann architecture. Von Neumann, possibly the most famous mathematician from the 20th century, or maybe this other guy, Alan Turing. So the von Neumann architecture is kind of not his singular invention, but idea of a stored program computer where there's a CPU, there's some memory, there's external storage, multiple inputs and outputs, and the data and the instructions share the same bus, and that's called the von Neumann bottleneck. So that's how most computers are built these days. Yoni was saying a bit about embedded systems. You'll get some embedded systems that have something called the Harvard architecture, where they don't share a bus, the data and the instructions, depending on what you do. And general purpose computers aren't the only thing. So another bit of a crappy example, but you know, cryptocurrency is a thing. You can see the development. If you have a very important calculation you need to do really, really quickly. When Bitcoin started, people just did it on their CPU, on their general purpose computer. They want to go a little bit faster, they start using GPUs. Then they want to go a little bit faster than that, they start using FPGAs. Does anyone know what an FPGA is? Or is that a bit so it's a field programmable gate array. So you can define the configuration of logic gates with software. So it's much more easy to configure a circuit. And then you go to ASICs, which is an application-specific integrated circuit. So it's sort of gone from general purpose computer, but to a specific thing where we just want to do it really, really fast and pump it through. So they all exist now. The strangeness of all these things has been bled away because we're so familiar with them. I don't even know I am, that in my life, you know, how bad computers were when I was a kid trying to download Doom off of BBS in the 1990s compared to now. The change is huge, and even the ability of networks to talk to other computers, to use hundreds of computers at once to do one calculation is not a thing I could even imagine back then. Okay, don't know how much more to say about this. Turing machine was, so Alan Turing did a lot of work on early computers. The idea of a Turing machine was he was trying to solve a particular mathematical problem, the halting problem. And he came up with a model, a mathematical model that allowed him to prove that, called a Turing machine. And you'll hear about Turing complete languages, which means it can implement a Turing machine. The Turing machine's a really simple device. I could probably, I'll just talk. It's basically just, imagine you have a bit of tape, it's got ones and zeros on the tape, and it has a little head that can read what's going on underneath it. So I'm above a 0. I have some instructions about what I'm going to do next, and I can either go left, I can go right, or I can read the thing, or I can delete it. And that's a Turing machine. And it's an abstraction of how computers work. A digital computer works at a low level. The thing is, programming a Turing machine is a nightmare. There's even a joke language, I'd say, you might have heard of it. I won't say what it is because I'll get in trouble. That is programming a Turing machine. Does anyone know what I'm talking about? One guy does. He can tell you later. Yeah, so it's a nightmare to think of, this low-level thing to this high-level thing. So the other thing I'd say about what a computer is a stack of abstractions. So you're trying to solve a human problem with this low-level thing that's digital computer, this Turing machine. To get to that is a stack of abstractions that are, build on one another. Now, one of the big things to understand when you're coming from mathematics, coming to computers from mathematics, is that the abstractions tend to be poor in computer science compared to the ones in mathematics. Low-level details become important sometimes, so you can't get away with not knowing roughly how things work underneath. Things will always leak through to a higher level. So knowing the low-level stuff is important when things don't work or you're trying to do performance. So there's no perfect implementation. These abstractions leak all the way through. Cool. I'll quickly take a 10-minute break. That sounds good. I'll come back and talk about this. That sounds good. I'll let you guys have a rest. Yeah. Okay. How's everyone going? Are they ready for round two? Yep, good. Okay, cool. I'm not. Okay. So finishing off there, computer, tool for mathematicians that ran away from them, and a big pile of abstractions that most people don't understand. So honestly, like I can say, working in this field, I don't know how many parts of a computer work. I have absolutely no idea. Rough mental model for how things work all the way up, but definitely not. Like some parts of it are a complete mystery to me. It's sort of too much information. So it's this thing in mathematics, the power of abstraction is really a beautiful thing, that you don't have to know the low-level details, which is where languages like Python are coming from, languages like Julia are coming from, that you don't, there's some things you just don't want to have to worry about. Hopefully it's clever enough that underneath the hood it will work really well. So the culture of software engineering though, software development. So in a similar way that the original computers were a room full of women, naturally the people who started working on the first programs were often women as well. Grace Hopper would be the first one. So this idea of like, you've got this thing that's acting like a Turing machine, all it can do is logic and read trues and falses. Maybe we want to turn that into human expressions in a way. So two of the oldest languages, I'd say, like COBOL and Fortran. Fortran has one-based indexing, just in case you want to, like, historical precedent for Julia's one-based numbering system. So this idea, these old languages like COBOL and Fortran, they both still exist. If you'll see some people in maths, I'm sure, who have supported a Fortran code base for years and years and years, and they're still using it now. When you get to do a project in, say, honors or something, you'll probably touch some Fortran code. COBOL still lives on in banks. I do work consulting with a bank, and they have this mythical COBOL mainframe that lives in the basement and everybody's scared to touch, and it's running code that nobody really understands for 50 years. These things exist. You hear stories about COBOL developers getting $2,000 a day to go and touch this code base if something goes wrong because nobody knows the syntax anymore. This thing, so anyway, I think I lost the thread of what I was talking about. What the idea is you're trying to manage complexity. So a software developer is someone who's trying to manage complexity most of the time, especially when you're a professional software engineer. All of these paradigms that come through in software engineering, what you're trying to do is convert a human concept into something that can run on a computer, do something useful. There's a big stack of complexity there. Your job as a software engineer is encoding that human problem into something the machine can understand and managing complexity along the way. I saw on the Piazza thing, a lot of you guys are getting the first-hand experience of managing complexity, trying to install iJulia and Qt's having problems because you've already got an installation of Anaconda. That's like day-to-day, that stuff happens all the time. It's actually a good and horrible experience of what it's like to be a software engineer. Managing environments, setting them up is actually a big part. And again, what you're trying to do all this time is manage this stack of complexity. So there's two aphorisms that are pretty famous in software. I think the first one's the Python guy, Guido. Code is read much more often than it's written. So when you're writing software, people are going to come back to it again and again and again. The way it works, it's like a problem is never solved and software is never done. Software is done when people stop paying for you for it, and that means they sort of don't care anymore. So it's actually a bad thing. So you'll always be going back to this thing. Other people will be coming back to this thing. So there's a little bit of tension here when you're doing something academic, because you know you're solving problems and they're one-off and then they're sort of disposable. It's not really like that. Like things haunt you for years and years and years. And there's so many stories in software of like a new guy comes in and he worked on someone else's code base that was like 20 years old and they asked some questions about it and it lives on much longer than you ever intended. I've had that in my career, things I wrote a decade ago, people are still using now. Millions of dollars still get made off this software. It lives forever and it haunts you. And I go to a meeting, a journal club, and people who work at the place I used to work at come and they'll complain about my software. And I was like, I don't even work there anymore and they're still asking me questions. So it's not really disposable. It's a thing that will haunt you forever. And this other one's sort of on the same thing. There's only two hard things in computer science, cation validation and naming things. And so it's sort of a joke that, you know, something fairly technical versus something seemingly trivial about naming things, but that goes to that other one. It's difficult. So I am an accidental software developer, I'd say. Coming to it from mathematics, I came in as a mathematics specialist and I learned how to code on the job. The experience when I went through undergraduate was they sort of just threw you in. They expected you to learn development secondhand and you make these horrible MATLAB scripts or Python scripts and they're terrible and you don't know anything about version control and reproducibility is not a worry. And then you go out and there's all these things you have to learn. So that's sort of what we're trying to address with this course is hopefully impressing the importance of some of that stuff for you guys. So, you know, I'm sort of managerial level now, have been for a while, is like when people graduate, as a mathematician, when you're graduated, even now, I would say you all look smart. I'm sure you're all very smart, that your level of mathematical sophistication will be much higher than the average software developers. So it's completely possible for you guys to blow everyone's minds on a daily basis on the stuff you'll come out with. And it will seem arcane and strange and difficult. And that's really bad because you'll be the only person who can support it. So this idea that you write software and it lives forever and it will haunt you. It will haunt you on your weekends when it breaks and doesn't work. If anyone's making money off of it and it breaks and you're the only one who understands it, that will ruin your life from personal experience. So you don't want to learn it the hard way. Yeah, so software engineers are, it's all complicated nonsense. I think a part of it's like I was saying, it's like you're making little artifacts, you're answering questions, and it's sort of disposable, and it's sort of back to front in how it works when you're doing software engineering for a profession. It's like, I think more of like when you're further up and you're doing research, you make a script to do a thing and you just want it to make the results for the paper and you never care about it again. Or you're doing your homework, doing your assignment, you never want to see it again. It's back to front. Like business people you interact with will care very strongly with the results. The other software engineers you work with on a day-to-day basis will care about maintainability and things like that will be a really strong focus. Harping on, but it's important. You guys are younger though, so coming through, it feels like a generational shift. People understand version control. You guys are getting exposed to programming from a younger age, so it all seems positive. One thing I'll say, just like for professional development, is when you're a mathematician in working in industry, you'll be like, do you have a skill that's useful everywhere? Like most people won't have the level of sophistication you'll have at understanding like, modeling problems and concepts. So you're going to be interacting with lots of people, like at all levels. You'll be interacting with business people, other software engineers, customers, people who haven't thought about maths since high school. How you communicate is, very, very, very important. And just for this course, think of code as another form of communication. So going back to this naming things being important, like stupid things like that. Like it's not like computers are resource constrained. You don't need short variable names. Say what a function does. This stuff's important. Even though it's simple, make it easy to understand. Even yourself in 6 months. If you go, it's often the case, it's the case for me all the time. In 6 months, I'll have to go back and understand this thing again. Will I be able to do it? Very hard to test for in a course like this, but I just want to say it at the start so you guys are all on top of it, which I'm sure you are. Andy's left because he'd be laughing at me because I am the worst culprit for writing terrible, horrible, hacky scripts that he has to live with. So that's fine. I'm the worst, do as you say, not as you do. Okay, cool. So we'll get back to actually doing some Julia stuff. So we'll start at the bottom. So digital computers we're working with, everything at a very low level is a logic gate that's on or off. It's a voltage that's 0 or 5 volts. You can interpret that as a 0 and a 1 in a Boolean sense. It's true or false. Again, back through this history, the invention of the transistor was a big deal. A lot of these early computers had valves, triodes and all these crazy things where they had mechanical switches or electronic switches that were really unreliable. Invention of a transistor blew everything away. Being able to have these things that switch and operate as logic gates is a big deal. So at a computer, again, pile of abstractions all the way down. The lowest level abstraction is a wire that has a voltage, a high voltage or a low voltage. And you can interpret that as a true and a false. So we call that one wire, one bit. A sequence of bytes, a byte is a sequence of 8 bits. Historically, that's a useful number. 2 to the 8 is 256 options. I hope that's clear. So we'll go through here. I don't know if I'll copy into a REPL, unless you want to see me do it. Actually, shout out if any of the syntax. Can you guys see this, or do you want it a bit bigger? It's okay? There's some syntax you probably haven't seen. I'll just be slightly aware that the syntax is probably unfamiliar. So Yoni before, can you guys see this? Too small? Fine, good. Yoni before, if you had an array, x equals 1, 2, 3, 4. He did for I equals 1 to length of x. That show xi. So go through the array to its length, print the I. usually when you're indexing into an array, something's gone wrong. That's not the normal way to do it. What you would actually do is you'd have an iterator for, say, xi in x at show xi. So you're not actually going I and then indexing back into the array. You're just pulling them off one at a time. If you want both, which happens every now and again, useful function to know, very similar to Python. Enumerate. So you can get both. Oh, that's a terrible array to demonstrate with, but if I say the same thing, but anyway. So we'll go back. That's just a bit of syntax. Hopefully that's clear. It's, yeah, I just say that usually something's gone wrong if you have to actually index into the array. Man, too many browsers. So what we've got the code here is we're gonna, this is just a statement that will print out all these things here. Oh, sorry, was it too fast? No worries. Yeah, in. So that, too many browsers these days. So you see Yoni, or Yoni wrote these notes. So for n in 0 to 255. This bit of stuff here is just to get this printing the dots. So if n is less than 18, or n is, that's or, those double pipes is or. Sorry, yes? There's a little thing there. You press in the Julia REPL. It's a bit hard to see. You'll go tab in blah. So you just type that in. Oh no. Sorry, guys. I'll make it a bit smaller. In. You just type /in and then you press tab and it will turn into the element of. Yep. So that's the little comment there, is how to get that. So same with the less equal. If you want to do that, or greater than equal, you can do GELE tab. Has Unicode support in Julia. So this is just to print out this stuff. So the main bits, this bit string function. We've got a uint8. Oh, sorry, I didn't even say what I was doing. Okay, so 8 bits, we're going to encode. So what we want to do is we want to turn bits into a number. So we'll start with the integers. So encoding a bunch of bits as an integer, there's lots of ways you can do this. A simple one is this way, where you're just going to go counting up. So 1, so we're going to go 0, then 1 in the bottom one, then 1, 0 for 3, 1, 1 for 4, 1, 0, 0 for 4, for 5, blah, 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 blah. You guys can read it out. The syntax here, this bit string will take a uint8. So an 8-bit integer in Julia is a type called a uint. Useful hint, if you're ever confused by something that comes up in Julia, just press question mark, you'll get a help, and uint8. Unit8. Uint8. So that will be an 8-bit unsigned integer. So what we're doing in this guy is going through the numbers from 0 to 255 and showing the bit representation of a uint8. So that's an 8-bit integer. So 2 to the 8 minus 1 will be the biggest one if we start at 0. All clear so far? That's pretty simple. This is one of the lowest types. Yeah, that's what it is. There's a hex representation, which we'll talk about in a little bit later. Oh, I got a question in the chat. Sorry, guys. It's confusing. The question is, what's so wrong with indexing into an array? It can be really confusing, especially when you're getting into index games where, if say you want to stride across an array, you know, this is a normal thing, like you want to jump by 4s or you want to jump by 5s, it can get really, really confusing. It's not wrong, it's just like, think about how comprehensibility. Sometimes you have to do it. Sometimes you don't have any time and it's easier to do it that way than thinking, but you know, not wrong. This is the stuff that comes across in software when you're doing software engineering professionally. It's like, there is a right and a wrong way, but it's more to do with taste, and it takes a little bit of time to learn. And most of the taste is informed by making it easy for other people to understand, if you can do it. Hope that answered your question. Yeah, it's keeping friends. Yeah, so, okay, that's that guy. That's the uint8. So you can have a 16. Julia has a whole bunch of uints. So you can tab and you'll see there's a uint, which is an abstract type. We'll ignore that for now. Different length bits. So you can have an 8-bit one, a 16-bit one, 32-bit one, 64-bit one, 128-bit one. Actually, on your physical computer, it has a register size in the CPU that has a bit size. Everything now is pretty much 64-bit. Back in the old days, not so much, 32 bits. There was a problem with addressing memory if it was too big. Sort of ran out of space, so everyone went to 64-bit. So sometimes it's nice to know like what's the low-level implementation size, because everything will be faster. And sometimes certain data formats will have different sizes. Talk about that later. Yeah, so different size bits, different size uints, depending on what you want to do with it. So we'll go to the next one, which is signed bits. So this is where, say you don't want to go from 0 to 255, say you want some negative numbers in there. So there's actually, this bit gets a little bit confusing because same with uints though, like you could do it any way you wanted. You could have a mapping that goes like 01, 01, 11 equals 1, and then any random thing, any random mapping going from bit representation to the integer interpretation. I'll go through this in a little bit more detail just in a second. So there's a particular representation that is useful to represent signed integers, and you'll see it here. So again, what we're going to do is we're going to look at int8s. So this is signed. So going from -128 up to 127 with a 0 element. You'll see the binary representation here. Now, a trivial thing you could have done is just have a signed bit at the start where you're going like, oh, 1's negative and 0's positive, and then just use the rest. That's actually not a good idea to do that, and I'll hopefully show you why in 1 second. Can everyone see that? So it starts with 1 up here and counts up from the bottom, then goes to 0s, and then it's like the uints above that. Is that clear what that's doing? Is everyone familiar with why? Anyone have any idea why you'd do that? Yeah, I guess why that particular representation? It's called 2's complement. Does anyone know that? One person. Yeah, it's yeah, you flip the bits and add 1 to do the 2's complement. The actual, oh, I'm looking at the wrong course notes, am I? Oh no, I have an old version here. No, that's okay. I will. Sorry guys, just a little bit of a. Okay. Oh, no, sorry, I've lost my place, that was all. Sorry, guys. Sorry, I was trying to jump ahead too far. Think about why you might represent the signed integers that way. We'll come back to it. Base 16 is really common. It's got a special name, hexadecimal. So it's 2 to the 8, so uses, sorry, 2 to the 4. So using a character, so in Julia, you can, and lots of other languages, you'll have a prefix notation. So if you want to represent a hexadecimal character, you can use this OX out the front, and just got some examples here. So these guys. So data, they're represented as uint8s, and they'll be displayed in hexadecimal. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and then it clicks around onto 1 on the front. Hexadecimal representation you'll see all the time. I jumped ahead too far, sorry guys. You can use the prefix notation for binary by putting an OB at the front. We've got a couple of examples here, so I'll just copy paste those. So 11, if we want to show, this representation equals, is this the same value as this thing? So it's true. So 11 and in binary 1, 0, 1, 1, and is x equal to OXB is 11 as well, and that's true. Another representation of numbers in a base that's useful. So, sorry, this is where I was jumping ahead to. I lost my place in the notes. So this finite range will do some strange stuff if you're not aware of it. So wraparound of unsigned integers. So say we've got the biggest element of this. So 255. And we're going to see what happens if we add 1 to it. Anyone got any idea what's going to happen? Oh. Yeah, it'll come back round. You can see it there. But so x plus u. Got to make sure I say the right type or it will promote it. Oh, sorry, did I do the wrong thing? Yeah, so we should see that there. Sorry, I'll just copy paste it. Ah, too much stuff. Sorry, this isn't so slick. So wraparound. So uint8 255. Oh, sorry, because I didn't have it as a uint8. That's OXF. So it'll wrap back round. So if we add x plus uint8 1, that's that guy. It will wrap round to 1, like you said. And signed integers, if we start at 127, and we add an int8 1, it will wrap back around to minus 128. Normal integer. So that's a uint. So uint is we don't say type 64 because it's the most common one, because most operating systems will be 64-bit. If I was on a different computer, so say like a AVR or something you might use like that's a 32-bit thing, that will actually promote to that will be a type alias for a 32-bit integer on that device. So it'll happen for 64-bit ones as well, it'll wrap around. So, okay, not so slick. So why does this occur? So again, at a very low level, how do we add? We've got logic gates. That's what a computer is at the lowest level. It's a bunch of logic gates and registers. So we've got an example here of how do you actually add with logic? So everyone, I hope, is familiar with the logical operations. So in Julia, what they look like, sorry, this will go off the screen again. So for and. So again, you can do the question mark, shift question mark. It will give you the description of what and means for this in Julia. And, or, but that's a short circuit, or you've got or, and not is a exclamation mark. So all of these are functions in Julia. So yeah, you can get help on what that is. So that's a negation. And another logic one we might want to do for this one is exclusive or. So is everyone familiar with what an exclusive or is, or can I assume that's okay? Anyone not familiar? No shame. No? Okay, so if we have an exclusive or, so we're going to have A equals true, B equals true, XOR A, B. What's that going to do? False, yeah. And for B equals false, we should see XOR AB is true. If we go B equals true, A equals false, XOR AB is true. And if, I could have just done it here, eh? This is easier. And false and false, that's false. So if we have 0, 0, we get 0. 0, 1, we get 1. 1, 0, we get 1. 0, 0, we get 0. You can actually think of that as addition modulo 2. Does that make sense if I say that? So if you're trying to add A plus B as bits, an XOR will give you the bit. So, okay, so that's the first bit. So if we're just trying to add 2 bits, you'd use an XOR gate. So if we have a bit string, we want to go through, and everyone should know how you add from primary school. You know, the same algorithm is probably a good way to inform. If you're going to add 2 bit strings, you're going to go add, add, carry, add, add, carry, add, add, carry, add, add, carry. That works the same in binary. So what I've given you an example of here is if we had a Boolean representation of a number, I'll just copy these functions across. How would we actually add the bit strings as if we were doing it in hardware? So this is kind of insane to do this at this level, but it's an instructive thing to do. So I've made some functions here. I'll go through them in a little bit of detail in a second, but first bit, okay, we're going to have 2 numbers A and B. So we'll go to this function. So the main function here is this add n digits. So I've snuck in a bit more syntax that's going to confuse everyone. I'll say that this isn't necessary to put this in. For this function will still work on integers without putting this stuff here. So this is called, so this colon colon t, where t is a subset, this little subtype, sorry, a subtype of the integers. That's this syntax. If I do this function without this type annotation, this is called type annotation. So it's telling, so Julia itself knows what the type of these variables are supposed to be. This function will still work for integers, but it will also work for other things I don't want it to work for. It doesn't make sense if these aren't integers. So I'm just putting that there mostly as a guard to stop people putting stupid things in there. If you've got a floating point number in there, this algorithm makes no sense. Or any other object, any other struct type. So that's sneaking a bit more Julia syntax in for you guys, so you'll see it there. Is that clear what that part means? You're all happy? Okay, cool. So this bit's a bit yuck. I just put this in here as an alternative for what you saw above in the notes about using bit string. So there's this function called digits that's a part of base Julia. And what it will do is convert between bases. So it will turn it into an array of a type at a certain base. So if it was 16-bit, we'd pad it with 16 and base 2 for Boolean. And we're interpreting A as a Boolean. So what you'll get is 1, 0, 0, 0, 0, 0. So if you had that bit string A, you get the same thing, but this is a string return this type. So it's just different ways to skin a cat. They do the same thing. I just thought it's interesting to see 2 different ways to do the same thing. You might want to do one sometimes, you might want to do the other sometimes. That's as a 64-bit because of the type of A at the moment. So, okay, so this is converting these 2 numbers to an array of Booleans. Okay, and then this is the result. I'm going to make it the same size. Fill is a function that is very useful. So fill it fills an array with a thing. So I'm filling this with bool 0, which is a bit silly, but that's just false, right? Again, seeing a bit of weird syntax, this thing I was saying about naming things and making things clear. I don't do that. I want you guys to do it. So we're going to fill, so filling the answer, that will make 16 empty bits. So what we're going to do is one at a time go through the bit representation of A, one at a time, go through the bit representation of B, and add them one at a time. So what you do is we have a carry. So as I was saying, you're going to add, carry, add, carry. If you're imagining the primary school way to add two big numbers, you go like, oh yeah, this plus this plus this. Carry the one. So for I in 1 to n, so because it's particular bit size, we're going to go through one at a time. And I've made this function called full adder, and it will get the ith reference of A and the ith element of B, sorry, not reference, and a carry of false. So the first one is false because we start at the end, zipping all the way up. Again, I said, you know, don't index into arrays, and the first thing I do is index into arrays. So ignore everything I say. So a full adder is composed of two of these half adders. So as I was saying, an XOR, so sorry, half adder is the first bit. So this is doing, the first part of this is we said if we add 2 base 2 modulo 2, add these two things, we're going to get an XOR for the first bit, and it returns a tuple of A and B for the carry. So the first one is meant to be, so again, if we're adding A equals false, yep, and B equals false. So you've seen the answer, but what's the only combination of A and B that gives you a carry bit? Is that clear to anyone what the answer might be? So if you have 0 plus 0, do you get a carry? No. 0 plus 1, do you get a carry? No. 1 plus 0, no. 1 plus 1, yes, you do get a carry. So that's an AND operation. So XOR for the first bit and for the carry bit. This is a way in Julia of defining a one-line function. It's got the type annotation in there too. So that's this half adder function. So we should see if we go half adder, and we're going to go, so false, false, oh, half adder. So false, 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 true, and true, false, and true, true. And that will give false, true. So 0, that should be all the combinations you get. So when you get, that's good for the first time you enter into this thing. You have to do this again. So every time, and then you go to the next one, you've got a carry bit where carry will be false. So I'll leave this as an exercise for you guys to show that this full adder logic is correct. So you could have just do the truth table for, I've got A, B, and a carry. What do I want for the value underneath for that bit, and what do I get for the carry bit? So that'll be a truth table with, instead of just being, okay, this one will be XOR, this one will be AND. What do you get for those three? So you have more combinations. Turns out, cut to the answer, it's 2 half adders ORed together. So this is actually a way of implementing addition on integers if they have a particular representation. So if you don't, so I was saying, like, why would you do the sign bit? Why would you do the signed integers in this particular 2's complement format? It's because you can use this adder on uints and ints. If you did it a different way, it might not work. So this problem of computer works with bits, I've got to represent an object I care about at a high level in bits on a computer, and I want operations to work on them. Being able to reuse something is quite nice. So being a little bit clever about how you represent things will save you time. This is called a ripple adder. I don't know if anyone's heard of that. Is that familiar to anyone? No one's done. This is the stuff that goes on a low level. So if you were going to, like I was saying before, if you had an FPGA and you're trying to implement addition, you might do something like a ripple adder. Anyone trying to think a little bit algorithmically, can anyone think of an immediate improvement to the way this is working? Like if you were going to design, if you're a circuit designer and you're going to go, I'm going to implement addition, what might be a trick I could do to make this faster? Or lower circuit depth? Yo. Yeah, the more you work with more bits at once is one thing they do, definitely. So this is the thing, I don't know how addition is implemented on a modern CPU. In the CPU will have an arithmetic unit. I don't actually know what happens in there. I assume it's some crazy thing someone very clever at Intel has worked out how to do a long time ago to add 64-bit integers together really fast. So, it's programming a computer sometimes is like arguing with a pedantic idiot. Like you have to be right all the time. And it has a particular idea about what everything is. And it gets pretty complicated. So not having to worry about representation of numbers as bits, what's going on underneath, most of the, again, I was saying about leaking abstractions, most of the time you don't need to worry about how addition works. As a human, all I care about is I know at a superficial level, at least mathematically, what addition means. I want the computer to do that. It has to represent numbers on the computer. Most of the time it will do the right thing, apart from this wrapping thing. It's always modulo, the size of your representation. It will come back around. So these are the these types of bugs will bite you when you're doing software, because your brain, like my brain, mathematician's brain, you'll think of mathematical objects and you want the operations you're doing to act like mathematical objects. And they do most of the time, but sometimes they don't. And this example of wrapping around and coming back underneath it's a feature of programming on a computer, one that comes up for integers. Is that clear? Any questions about that so far? Cool. Okay. Okay, so here's just, if you run, I'd recommend you copy this code into your own Julia session, run it, see if it's broken. If there's a problem, like Yanni was saying, make a GitHub pull request and tell me what's wrong with it. I'd be happy to know, actually. Yeah, so it's nice having this as a source code repository. This isn't a fixed set of notes. If you find a problem, please let us know. This is doing it on 16-bit ones. If we add, you should see this come through. So if you think of this ripple addition, you go 1 + 1 is 0, carry the 1. 1 + 1, 0, all the way through. It will wrap around and come through. So, so this is a seemingly simple operation. So when would you actually need to worry about doing a function like this is when your integers got really big. So if you've got if you're trying to do more than 64, 128 bits, and the hardware can't do it anymore, you might need to implement this yourself, or part of Julia would do it for you. So these things become important. I think I'm shadowing to Paul's section where we're going to have very big integers. And what addition, like how you would actually implement addition on arbitrary precision things. So you might want really big numbers to come through. So I'll say for you guys, as an exercise, maybe some of you know already, but how do you think multiplication might work? What's your, not you, he's just answered. So elementary school algorithm for addition was fine. Is that fine also for multiplication? Do you think that's the best thing you could do? So again, if we think about, addition, we're going plus, plus, carry. So multiply, you'd go times, times, carry, all the way along. Put a 0 underneath. That's a much more intensive operation to do. The primary school algorithm version of multiplication is much more intensive than addition immediately. So you need a bigger circuit to do that. And if you're doing numbers bigger than you can fit on the CPU, so more than 64 bits, it becomes important to think about how you might actually do that operation. And if there's something more clever you can do, and the answer's already up in the chat, but yeah. 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 No, that's definitely a valid option. So it's if it was small and you knew it, you could just do it multiple times. It's this thing of like, if you know something about your data, you can do something simple. Like if you know, say you're only ever multiplying once or twice or 3 times, and that's all you're ever going to do, you might do something special with a big number. You might just add it 3 times in a row and done. So that's a good point. So knowing something about your data is a thing. General. Does anyone else have their hand up? I thought I saw someone else. No, anyway, I'll leave that as an exercise. Paul's shouted out in the chat what the actual answer is, so you can just copy paste into Wikipedia and you'll know everything coming up in the course. Cool, so that's what I'm saying. So also exercise left for you guys is to think about how many operations are required for this thing. So basically we're going through this array one at a time, 1, 2, 3, 4, 5, 6, up to the bit size representation of it. And we're doing a bunch of logical operations. So there's an XOR, there's an AND, calling this thing twice. So we do those twice and then we OR them together. So it's proportional to the size of the bit representation. How long it's going to take to add these things. So when you're doing it in a circuit, the thing that actually defines the depth is how fast this thing called a propagation delay. So I'm going to put these voltages on, it will flow through, and then I can get an answer out. So one of these things that's hard to understand about modern computers is how fast the clock speeds are. It's like gigahertz. So I don't know, any of you guys off the top of your head, who knows what the speed of light is? 3 times 10 to the 8. So in a nanosecond, so if you're on a 1 gigahertz clock, how far does light go? So it's like a human-sized distance that it's like 30 centimeters or so. If it add a nanosecond, so if you're at 3 gigahertz, light only travels this far. So these clock speeds, and you're doing these logical operations, the path length that the electrons, the electric fields propagate along, you know, we're pushing the size of these things, how fast they can actually switch, and you can see something happen. My head explodes when I think about that. So when I was young, you know, 10 megahertz clocks and stuff. When the first computers I was using, 20 megahertz clocks, they're up to gigahertz now. So you can't have too many logical operations in a row, or your clock speed's not going to be enough for the field to move through in that time. I think I had a point, but I've lost it. So again, thinking about complexity of like, this is a way of doing addition. Is there another way of doing addition? Is there a better way of doing multiplication than just the elementary school algorithm? These things really matter. If you can imagine that, so how much code runs on the internet doing things like addition and multiplication? If you make a small difference to performance, you're actually making a difference to how much CO2 goes into the atmosphere. It's crazy to think on that level. Like, these algorithms do matter. Okay. Any questions on that bit? I'll leave it. That's just a prelude to thinking about complexity and thinking about algorithms. So where are we going? So, okay, binary data as a string can often be considered to hex. So here's this other, we'll go for this other one. So again, I don't really know what happens on a CPU. There's some simple operations you can do. You can do logical operations. One of the useful ones you can do is called a bit shift. Does anyone know what a bit shift is? Someone does? No? No one wants to say. So it's basically just taking the register and shifting it all a few positions to the left. What you can think of, so we'll take a number in binary 101. So that's 5. I should have known that off the top of my head. So we'll just do these show. So not too much at a time. So as a bit string, it'll be 1, 0, 1, blah, 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 blah. If we do a shift operation, the syntax for a bit shift operation in Julia is this. 2 arrows in the direction you want to go. So if we shift it across, and we probably want to do what the bit representation of that is. So bit string. So it's just shifted it 3 across. So you could do bit shift 2 and 1 and 0. That's a bit shift operation. This is one of these low-level things that the CPU can do and knows about. Why that's useful is that it's dividing or multiplying by powers of 2 approximately. So too much stuff at once. We'll do that one at a time. So x equals 2 to the 4. And if we go 2 times x, 2x, you're allowed to do that. That's multiplying by 2, we get 32. If we do x bit shift 1, it's times by 2. And if we do x divided by 2, we get, oh, sorry, I should point this one out. So anyone notice what happened there? If I did x divided by 2, what happened? Does it look a little bit funny compared to what happened before? So x times 2 is 32, but x divided by 2, I'll get there eventually, is 8.0. There's a little hint if we go type of. So a useful function in Julia is type of. We'll tell you the data type that's being used to represent this. So that's an int64. The original thing was an int64, 64-bit integer. When we do this divide by 2, something sort of magical's happened. It's gone, oh no, now it's a floating point number. Julia will do automatic promotion of data types to give you the answer you want, sometimes if the method's implemented. We'll talk about this a little bit later. This can bite you. So before I was saying about type annotation, this is one of those things that will happen. This will come back. So Julia is a little bit magical. It's a dynamic language like Python. Promotion sort of happens all the time. Sometimes you want it, sometimes you don't. This is a case where we don't actually want it. So if we do this double slash, that's actually shorthand for integer division rather than division. So you should be able to see that again. If you're ever confused by syntax in Julia, go shift question mark, we'll go divide. It's right division operator. It says exactly what it's doing. Multiplication of x by the inverse of y on the right. It's a little bit weird as to why it says it like that, but hopefully that'll be clear a little bit later. Next lecture, we'll start going through some of that stuff. But if we do this, we go for help / divide 2 integers or rational numbers. So this is kind of cool that it will do, x is a power of 2, as we started with, so it's 16. So if we divide it by 3, say, we get a rational number out. So, and we'll just see the type of that. So that's a rational. So you have all these data types for numbers that are useful. There will be some sneaky promotion and conversion that happens underneath if you're not watching what you're doing. So if we want it to be an integer, we do this. So what we should be able to see is that x divided by 2 equals 1 on 8. And if we do a bit shift, we get 8 as well. So this is a really fast way of multiplying and dividing by 2. On ints is a bit shift operation, which is a useful operation to do. So in your algorithmic toolkit, if you're ever doing low-level stuff, these are the sort of operations you're going to do everything with, is bit shifts, XORs, ORs, ANDs, blah, 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 all those logical operations. Any questions? Any questions on that bit so far? So it's a useful thing. We'll come back around. I'll show you a neat trick that somebody came up with for using these bit shift stuff. Here's a useful function. We don't have much more time, so we'll just go quickly through that. So size of is a function in Julia. You can read the help yourself, I guess. I'll just try and make this a little bit bigger. Oh. Failing on the size of the screen. Too much stuff. Okay, so for a particular data type, it will give you the size in bytes of the canonical binary representation of a given data type T, if any. Size in bytes of an object is not a data type. So I've got a couple of examples here. So I'll just run through those one at a time. It will give you the answers. But this is a useful thing. So one of these abstractions that you can never run away with, never keep out of your mind unless you're doing simple scripts is like size in memory of objects will bite you. You will end up making lots of stuff if you're not careful, and you'll use all your RAM and your computer stops working. It's one of these abstractions you can't get away from. So knowing about the size of things is useful. So for int 8, size of, show x, size of x. So because it's an int 8, it's in bytes, so that's the 8 bits. It's got a size of 1, and its value is 120. Whereas if we go for 120, that will be a 64-bit one by default. So we go type of x is an int 64, and we go size of x, 8 times 8 is 64. Okay, so a string. Anyone want to hazard a guess as to what size of x is going to be in this case? So this depends on how you encode strings. That's something we'll talk about in a little bit. So it's the size of 5. So each character will have a 1-byte representation. So each character maps to a 1-byte thing. You've got enough options to pick out the characters there. So it's an array of length 5, 1, 2, 3, 4, 5, and then 1 byte per character. Yeah, let's see the rest. So H, a normal character size of 1. We've got alpha in here, which actually comes out as the size of 2. So again, if you want any numerical characters, again, like before, /alpha, and then press tab, and you'll get alpha. Same for any LaTeX sort of string. Beta, gamma, they're all in there. So this character representation of alpha has 2. Okay. So this is another useful function. So before I showed you guys fill. For things you might commonly want to do a lot of, there's functions like ones or zeros is another one. You give it the data type and then you say how many you want. So this will make an array with 1 element in it of 1, and then 2, and then 3, and then 100 in this example. And we should see the size of x, because it's a uint8, will be 100. So hopefully I've made 100 of those, 100 times 1 byte for every character, because it's uint8s. And there we go. So this guy will be a floating point number. So I'll say a little bit later about what floating point numbers actually are. You might already know, but size of x for this guy, anyone want to hazard a guess what it might be? I'll just do it. It's late, 8 again, so 64-bit representation. And if we do ones, that will default to float 64. So we'll see that in the type. So it's a vector of 1,000 elements of float 64. So size of this guy will be 8,000. So 8 bytes times 1,000. Okay, so I think we're on 7. That's a basic introduction to some really low-level data types. Hope that was clear. Hope it wasn't. Some of this stuff's a little bit, it's a little bit painful, but it's good to know. The things that will bite you are things like this wrapping. Knowing that this is a thing that happens will save you. You'll get bugs from this when you write real code. Okay, any questions? We're good for next time?
Next time, tomorrow it's
6. Okay, cool.
I like it. I'm going to steal your history lesson for my class on Friday.